Okay, so
Um,
hey everyone, welcome to our first December talk. We have Costa from Drexel University, who is the lead developer on CleanRL, a very great library for doing like distributed RL experiments. And Costa today is going to present on how they got PPO to not suck at scale. I think is a very important topic. So,
yeah,
Costa, if you want to take it
yeah,
from here.
yeah, sounds good. Yeah, thanks, Louis, for the introduction. Yeah, let me go ahead and share my screen. And can everyone see my slides?
Yeah, I can see them.
Okay, awesome. Well, I'll just get started then.
Mhm.
Yeah, so today I'll be mainly talking about PPO. Louis did a fantastic introduction for me. I'll add maybe a little bit more. I'm a fifth-year PhD student at Drexel University, and my research area is in deep reinforcement learning with a special focus in reproducible and efficient deep reinforcement learning algorithms. I maintain CleanRL, which is a collection of very readable deep reinforcement learning implementations, and we're able to scale it to hundreds and thousands of games. And yeah, so in this talk, I'll talk about how I try to understand PPO in the first place, talk about some of the difficulties there, and then I'll talk about how I try to reproduce PPO. How do I ensure the reproduction is correct by using really good documentation and benchmarks? And then I'll talk about our optimization efforts by profiling. So we look into the amount of time PPO spent on different things and try to come out with different techniques to address these bottlenecks. And I'll also talk a bit about, excuse me. I'll talk about a little bit of connection with ChatGPT. ChatGPT is very new to me, so I'll be making some guesses and comments, but I would love to hear your thoughts as well. And then I'll talk about RLOps, which is a way for you to ensure that your new feature or your new optimization do not break your existing code base, which I think is very important, because the last thing you want to do is to create a feature, make a new release, and then 1 month later, someone raised a GitHub issue saying, hey, I ran your code and it gives me like 0 scores or something. So RLOps will help you avoid that type of issues. So we'll do a quick recap on PPO. PPO is a policy gradient algorithm by OpenAI, and it has been applied to a bunch of high-profile tasks, such as Dota 2, OpenAI 5, and then ChatGPT, InstructGPT. It's also being used in microchip design. It's been cited thousands of times. At its core, PPO is a policy gradient algorithm, and the basic intuition behind the policy gradient algorithm is that you want to increase the likelihood of executing an action if an action results in better returns. So, right, that's pretty straightforward. It's like if you did something that results in really good results, you want to do that action a little bit more with a higher probability. And the PPO proposes this clipped policy gradient objective. But really what it's doing is to ensure you can use the data for multiple times without making your policy to diverge too much. So that's one of the core contributions of PPO, is to ensure the policy is within some sort of trust region empirically, so that you don't have a completely different policy after a single update. That way, your policy update is relatively stable. And then on top of that, PPO is an actor critic algorithm, so it has a value function as well to try to estimate the value of the states. So during the overall loss of PPO, you also have a value loss, which is typically a mean squared error. PPO actually does a little bit differently. It does this clipped mean squared error, but there's no evidence that it actually performs better. So I don't know why they added it in the first place. Maybe it performed better in some selected tasks, but overall, I haven't seen enough evidence that this performs better. And it also has an entropy loss, which is to increase the chaosness of the probability distribution. And some argue that it increases the exploration potential of the algorithm because the action space is a little bit more chaotic and you're more likely to execute actions that you have previously have not explored yet. And if you read through the PPO paper, it has a pseudocode, which looks pretty simple at its core. And that has been my experiences as well, is that the paper seems pretty straightforward and it makes you feel that you can just go in and do the implementation and everything, it works. But the sad thing is it doesn't. So if you sort of follow the pseudocode over here, it's actually really tricky to understand a lot of terminology that they use. And the pseudocode that it provided is, there's sort of two things to it. First, PPO from OpenAI has sort of two versions. The original version is more in line with what's being presented in the pseudocode, but the more popularized version, which is PPO2, PPO2 is what's used for ChatGPT, and PPO2 does the architecture a little bit differently, even though the core idea is still the clipped policy laws. So part of my work is to summarize 37 implementation details of PPO, and here is sort of a more accurate source code, more accurate pseudocode for PPO. And as you can see, there's actually quite a bit of components to it. But I think it might be helpful for us to maybe go through it, since it's only about 30 lines of pseudocode over here. But essentially, you want to, initialize end environments in parallel environments. That's sort of the core innovation in PPO2 is that you initialize multiple copies of an environment so that you learn in a batch environments fashion. And then you initialize some policy parameters, you set up the optimizers and stuff like that. Then PPO, it does something like learning rate annealing, but it has two phases, roughly speaking. It has a rollout phase. And in the rollout phase, you collect data in your end environments. So imagine if you have 8 environments, and then you would collect 128 steps of the data. So you're collecting 8 times 128, which gives you 10,024 data points. And then all of those data points are being stored in your storage. And then here comes the learning phase. So you try to calculate advantages to returns, and then basically you're going through the PPO epochs to do the training. And then during each epoch, you're also doing mini batches. So even though PPO is an on-policy algorithm for the most part, once you did the first gradient pass, it actually becomes an off-policy algorithm because the policy is that you're optimizing for is no longer the one that's used to collect data. But that's where the clipped objective comes into play because it ensures your policy is not diverging too much. So that's the main idea of PPO. And by the way, so I'm doing this presentation in sort of a casual way. If you have any questions, feel free to interrupt me. And yeah. Yeah, so one of the things that really helped me understand PPO, and before I had a really good reproduction of PPO, I went through a lot of wrong paths, if you will. So I tried to implement according to the paper and resulted a version that still could work really well in a lot of scenarios, but it's limiting in a lot of ways. So at the end, what I realized I needed to do is to just go through the OpenAI baseline source code. So that's sort of my tip number one is that you should, if you cannot reproduce the algorithm to a degree that to match the reported performance, one thing that you can do is to sort of go through the source code of the original implementation. And I did this thing where I keep a list of things. So If I see something that I don't understand in the original source code, I record its permanent link to the source code where this thing I don't understand, and I put it in my Notion document. So I just keep going until I have a good understanding of everything. So just sort of a technique to help you understand complicated code base. And eventually, I try to simplify everything into what I call single file implementations. And I think that really makes everything a lot clearer. And that's sort of the core idea of CleanRL, is to have these self-contained implementation that's easy to understand. And most importantly, everything is self-contained. So if you look at our import statement, we're not importing from CleanRL. There's no import CleanRL really. We just import from known packages, and everything is self-contained, but it's also highly readable. So for example, if you look at our core PPO implementation, it's only about 300 lines of code, yet if you run it on carpal, it produces the same performance as OpenAI baseline. So it's only 310 lines of code. And the way how you use CleanRL is you sort of use a file diff. So if I want to understand how PPO work with Atari, I just sort of do compare selected. And it tells me that if I want to work with Atari, I just need to add some Atari preprocessing wrappers. I need to change the hyperparameters a bit. I need to apply these wrappers. Then I need to change the neural network a bit because in carpal, it has sort of a box observation space. It has a vector observation space, whereas Atari, you have a pixel observation space. So something needs to be changed over there, but everything else is the same. So this way, I think it's really clear to the users as to exactly what you need to do to perform different tasks. And it doesn't present all of the complexity of PPO to you at once, right? You might think, yeah, but it's sharing a lot of source code here, right? Why don't you just make a modular library? Well, yes and no, because sure, I can, modularize this part and it'll be fine, but things get more complicated when you want to support new features. Like if you want to support LS10, all of a sudden, your batching logic needs to be changed completely. Because when you're not doing recurrent neural networks, what you're really doing is you don't care about the order of the training data. You can just shuffle all of them. But if you're doing recurrent training, you want to preserve the sequential nature of PPO in different environments. And this is just to deal with recurrent networks. When you have something like let's say, GPU accelerated environments such as Isaac Gym, then all of a sudden you need to do a different set of things. So for example, what you needed to do is you need to ensure the rewards are no longer transferred to the CPU, and the actions are no longer transferred to the CPU, so you don't deal with CPU ever. So you can imagine if you want to deal with all these kind of use cases, your modular implementation, modular PPO implementation is just going to bloat. It's just going to have more and more functional arguments. So I think in that spirit, I think CleanRL is sort of like to show you, this is PPO by examples. I just give you a bunch of examples of PPO, how it's supposed to work. And you're supposed to just be able to copy this source code and just use it for your own task. And because CleanRL's implementation is pretty minimal, it actually runs really fast and allows us to try out different prototypes really quickly because we don't have a burden of a modular library. We don't need to say, if I want to change one thing, I need to refactor a bunch of other things to even get it to work in the first place. In CleanRL's code, I just make a copy of this file and did some tweaking, and so the prototyping is much faster, but there's also a lot of challenges. Like there's a lot of duplicate code, but we have tools to help us manage that. So for example, we have tools that automatically sort dependencies, formatting, and so on and so forth, so that you don't see things like this. You don't see that there are some more spaces over here. So in general, the kind of spirit here is we want to minimize the lines of code differences so that the code base is still very manageable. Yeah, so that's a quick overview of single file implementations. And we think it really helps us to organize, to help us understand the algorithm. And another benefit is if you have a bug, it's very easy to diagnose with single file implementations because the bug must be somewhere in this file. It's staring at you, versus if you have a modular library, especially heavily abstracted ones, then it could be anywhere. You could be chasing a ghost in 20 files, and it could be very difficult. So yeah, it's really concise. It's easy to read, debug, and modify. It also makes it really easy to attribute performance and compare. So imagine you're doing a refactor and you introduce a new bug or something, and then you hit the performance regression. How are you going to diagnose that? Well, with this sort of programming paradigm, it's pretty easy because you just do a file diff. You can imagine you have a new version of this file, and then you make a comparison between its past version, then you notice, oh, the learning rate is a little bit different. That's how you sort of catch a lot of errors. And because we do experiment tracking every time we run them, so attributing performance, understanding regression has never been a big issue because we can just keep going back in time and compare the single file variants. Yeah, no duplicate. A lot of duplicate code, no unit tests. There's something you can do about unit tests, but I'll talk about that if people are interested. The next thing I think is super helpful to create a code base that's maintainable and understandable is you want to give really good documentation. So for example, in our PPO documentation, we always try to link to the original paper or related resources, be blog posts or Medium articles, whatever is used or whatever helps we create this implementation in the first place. Then we also included uses and instructions, how you're supposed to install it, how you're supposed to run it, some basic documentation and so forth. We always add explanation of the log metrics. So we have a list of metrics and we say what those are. And that's something that I feel a lot of RL libraries is sort of missing. And you see a bunch of metrics and you're only guessing, oh, it probably means this, but in fact, it could mean something different. So I think having these documentation is super helpful. Then I also have this section on implementation details. So if there's anything that is not mentioned in the paper, I put it in a list. So list is super helpful. It just tells you, oh, this is something that's different. Or something that you did that works better or whatnot. And whenever I can, I try to link to the original source code of where this is defined. So that way, I see Lewis's comment. By the way, let me just look at the comments to see if I chat to see if I miss anything. Yeah, yeah. So that's super helpful. And then we always have rigorous benchmark. So we always have a commands to rerun the benchmark for you to reproduce results, and it gives you these charts, and we always compare to reputable resources. So for example, PPO, we compare to OpenAI baselines implementation, and we create a table, and we always include the learning curves, and we always include the tracked experiments and then the agents gameplay videos. So yeah, it looks a little bit like that. Yeah, so that's that. So given all of these, we had a really good understanding of how to reproduce PPO because we understand its implementation details. We had good benchmark. The benchmarks are like evidence that says you had a good PPO implementation. Otherwise, you could be implementing PPO according to the paper or whatnot, but then you could be lacking certain features or something. So benchmark for me is really something that I look for in an RL library because it's evidence showing me that your stuff actually worked. But yeah, once we're there, we have a good understanding of how PPO does its job. My next step was to sort of try different techniques to optimize PPO. And I like to use a breakout as a good benchmark environment because it's not as simple as Pond that almost all RL algorithms can solve, but it's a little bit more subtle. And then if you see a performance regression, you always see the performance decrease. Usually with PPO, you get about 400 scores after 10 million steps. But if you see a performance regression, it would not be nearly as good. You'll be seeing scores like 100. So for me, it's a really good environment to just do tests and iteration. And this is sort of a list of prototypes that I've done in the past. I have this good baseline experiment that is tracked, and then I just included in the charts, and I keep adding new stuff, new experiments to it to see if I can gain the same level of performance while using less time. And I think that's sort of a very important distinction when we think about distributed reinforcement learning. Currently, a lot of distributed RL library, they talk to you in terms of FPS, frames per second. They're saying, oh, we can do 10 million, 100,000 FPS or 50,000 FPS or 1 million FPS. That seems impressive, but if you think about using FPS as a metric, it's not really that great, because imagine you have a random policy, right? You could have 100 million FPS. It generates 100 million data points for you, but the quality of the data depends on the policy that is used to generate those data. So if you have a random policy that generates 10 million data points, that might not be very different from if you just generate 100 data points. So I don't think using FPS is a really good metric, because the data quality is dependent on the policy quality. Therefore, I think almost 100% of the time, the better thing to ask is, given 100 minutes, how much can I learn? How many scores can I achieve with PPO in certain tasks? And I use weights and biases. So this is sort of my PPO zoo. And I organize them by run sets. So here I have different run sets, and then I see a lot of their losses. And losses is also something that I use to ensure my reproduction is correct. They always have a certain shape to help me understand, it probably looks good. So before I talk about these variants, I want to talk about the profiling that I did to give you a sense of the performance characteristics of PPO. Excuse me. So over here on the left is right. So on the right is the pseudocode, and this blue box representing the code that we're trying to profile. So we may have 200 iterations, and we're counting times in these blocks. So the yellow blocks is really easy to see. It's just learning. It's just a learning phase. And it does, in the case of Atari, it does 4 epochs and then 4 mini batches. So you're looking at 4 times 4 equals 16 backward passes. So that's all of these code over here, and it corresponds to this yellow time. Okay. And over here, you have this purple, which corresponds to inference time. So you are given an observation, and then you're sampling an action from the policy, and you're also calculating the value of the current state. And we have 8 environments. So every time you're giving a batch of 8 observations, and then you're sampling 8 actions. So this purple blocks corresponds to the inference time. And then you have the environment execution, which is this black box. So it gives you the next observations. So you do this purple block for 128 times, and then you do the black blocks for 128 times. And then we sort of sum up their times, and that's what's shown over here. So for example, when we look at the for loop approach, which is how we parallelize the environments. So over here, we are creating a vectorized environment E containing n equals 8 parallel environments, but how we parallelize environments is something that we can optimize. So a naive way is to say we just run a for loop for environments in my environments, environment.step, my action. So that corresponds to this for loop approach. And because it steps the environment sequentially, the environment stepping time is like a significant bottleneck for the algorithms. And you can see the training time is really, doesn't really take a lot of time on a grand scheme of things. Some other times, including like learning rate annealing, some caching storage, things like that. And in the for loop approach, we see each iteration. So this entire blue block takes about 1.2 seconds. But then there's a lot of things we could do. So for example, OpenAI Baseline's PPO, they said, oh, instead of doing this dummy vectorized environments that just execute environments sequentially, I could use sub-processes to execute those environments. So as you can see, once you do that, the environment step time is reduced significantly, and you're looking at over here. And then the inference time, the training time, everything else is still roughly the same. And our previous work called MPL, which uses C++ thread pools under the hood to execute this parallel environments, reduce about 80% of this environment step time of the sub-processes. So you can see the environment step time is reduced even further. And all of these three variants over here, they're being trained by using Torch. And then this is a time where JAX is getting more popular. So I tried using JAX as well. And surprisingly with JAX, the environment step time is increased a little bit. I don't exactly know why. It could be as simple as the way how JAX utilize CPU. Maybe there's some sort of racing. JAX is competing with MPL's computational resources or whatnot. But overall, we see a reduction of the iteration time. And then you see the training time it's not really a significant bottleneck. But I think it's because it's a little bit tricky how you measure time execution in JAX because of the asynchronous dispatch. So you see the other time over here is a little bit more. But anyway, it's a little bit difficult to measure. The bottom line is the overall iteration time is reduced. Then we try this thing called XLA interface from MPL. And how that works is over here, when you step the environments, usually you need to, when you sample an action from the policy, the action is given back to the Python control loop. And then the Python executes those environments in the environments. But what the XLA interface gives you from MPL has an XLA interface that essentially allows you to JIT the environment execution. Under the hood, it's implemented as some sort of black magic that still executes environments on the CPU side, obviously, but it uses XLA bridge to copy the data from the CPU to the GPU. But the bottom line is you can use a JAX-like interface for MPL, and it allows us to fuse the environment step time and inference time. That's why you see I use a gradient color over here, because the inference time and the environment step time are sort of fused together. And as you can see, when we use the XLA interface, we're able to reduce the overall iteration time further. And this is obviously that we have ensured that they have reached 400 scores in breakout. So we're getting strictly the same level of performance with strictly lesser time, right? So this is sort of a know what you're optimizing for. You're not really optimizing for FPS because, like I mentioned, it's not a good metric. What you should be aiming for is to get a certain level of performance, but try to reduce the time as much as possible. Let me see if there are new chats, if there's anything that I missed. Oh, thank you, Jeff. Yeah, so I read a little bit of RLHF, and that's something that I want to learn more from. Unfortunately, yeah, these couple of months just super swamped with a lot of other things. but I think JAX should still be able to help based on our prototype evidences, because even with RLHF, you're still doing a lot of inferences, and in JAX, inference is a lot faster, and then training is also a lot faster. And in RLHF, you probably don't have the environment step time, so you can sort of ignore the black color over here. And yeah, it just seems that JAX is able to speed up things a lot, and JAX is a really really good framework in terms of scalability. It also gives you access to TPU as well. So it seems to be the case that it will unlock a lot more possibilities for RLHF, and it seems that OpenAI have built their entire stack using PyTorch. So this may be some alternative tech stack that you all might be interested in giving it a try. But yeah, so that's RLHF. And then I also want to talk about, so I see Avnish had a question. Have you had the opportunity, so his question was, have you had the opportunity to test the scalability limits of CleanRL's PPO? Curious to know how many nodes, GPUs, CPUs people have tried run this on. So that's a really good question. So we tried a lot of things, so that goes back to our PPO zoo, right? So we're given a really good baseline over here that's using CPU sequential environment execution. And we actually have GPU. So this is multi-GPU. This curve right here is multi-GPU. It uses 2 GPU, and it's a little bit faster than using a single GPU. So I guess my question to this is, I don't have a problem with trying to scale it to more machines and whatnot, but I think there are 2 things to keep in mind. Is that when you scale to more machines, there's more overhead. Sorry, let me dial back a little bit. What are the 2 things that I wanted to say? Right. So the first thing is, I think you should create really good benchmarks, because using multi-GPUs and things like that doesn't necessarily always give you good performance, because you might have overhead or something like that. And so you should always have a benchmark that shows you exactly what are the benefits that the multi-GPU or multi-nodes has given you. And you don't want to measure it in FPS, because FPS is always going to be faster. So you want to use other metrics to measure it. And second of all, basically what all of these lines is showing is, at least in Atari games, right? This is obviously a simple example. There's a lot of techniques that you can do to improve the performance significantly without resorting to multi-GPU or multi-node, right? So for example, once we use JAX, it's just a lot faster than even the multi-GPU setting in PPO. Right. So those are things that I think it's good to keep in consideration, is to understand the bottleneck, understand the benchmark, and understand the effect of different things. I don't think a multi-GPU is something like a magic that just gives you a lot of speed, but it requires a very scientific way to do benchmarks to compare these experiments to know what works. Seeing more comments. Let's see. Typically, I think about reward per flops. Yeah, that makes sense. Yeah. Yeah, exactly. So you should, using reward per flop will be a really good metric, because reward is something that you ultimately care about. Yeah, sounds good. Then I'll talk a little bit about RLOps. So if you add a new feature, right? How do you know that new feature can still, how do you know your library can still reproduce the performance, right? This is such a simple question to ask, but I need to withhold my temptation on looking up libraries, but Yeah, it's very easy for you to just add this new feature and you think, oh, because I improve the storage or use the more better architecture and I tested it out, it worked on something. But how do you know if you can still reproduce the reported results? That's a really good question. Because sometimes you don't. Maybe your new feature or your bug fix introduces something like a silent bug, but there's no way for you to tell it. So what happens in CleanRL now is we introduce this technique called RLOps. We do a bunch of things that eventually allows us to do this. That says, I want to compare the experiments in CleanRL from the OpenRL benchmark project entity, and I want to get the DDPG experiments that is conducted by GEL, but it has a tag called RLOps pilot. That's the first set of experiments that was ever participated in this project. And I want to compare this set of experiments to PR 298, which PR 298 introduces a bug fix. And I want to see exactly what is the effect of PR 298. And it generates this for me. So it gives me a matplotlib frontend, which tells me the performance characteristics of new things that I've added. And it also generates the weights and biases report. So by using the new weights and biases report API, which is really cool because this is static. It's pretty good for overview and writing papers because you might need to do quite a bit of customizations. But weights and biases report gives you more interactivity. Yeah, nice. I saw, Lewis, you have the toolchain as well. Yeah, it absolutely helps. But yeah, overall, I think this is super helpful because it allows you to compare different versions of the library. And that's important because you want to give evidence that your library still works, right? Otherwise, you might have smaller test cases, but if someone tells you, I want to use your library to reproduce something, you might not exactly be able to reproduce that if you haven't done something like this to really validate the performance. So as a result, in CleanRL, we can always say confidently that whatever you see in the reported performance, there's a command for you to run and you can always reproduce this because every time we separate the changes into two types of changes. The first type is performance impacting change. So if you're changing something like a gamma from 0.98 to 0.99, we want to rerun the benchmark because that could impact the performance. And there are other types of changes like non-performance impacting change. If you're renaming variable, fine, you don't need to rerun the experiments. So that's sort of the basic principle behind it. Yeah, and I think that's about it. Yeah, so sorry, a little bit of background for this RLOps thing. The idea is when we run experiments, we just tag them. We tag them with the git tags, and we also tag them with a PR number. And then we can use this sort of syntax, like HTTP request syntax to sort of filter out the experiments. And it actually works not just in CleanRL, but we're working on this project called OpenRL Benchmark that basically we now have metrics from CleanRL, JAX-RL, some stable baseline 3, OpenAI baselines. So we can execute a lot of filters. So I can say I want to grab the OpenAI baselines experiments. I want to grab CleanRL's experiments. It generates the entire suite. And I can grab TQC from the TQC algorithm from stable baseline 3, and it's going to generate a figure like this. So yeah, it's just I think it's just kind of a general weights and biases front end for line plots. But yeah, so that's about it for the presentation. Any questions and things to discuss, thoughts?
This was fantastic. I can tell you for a fact that all of our engineers are like buzzing in our group chat right now. So
Awesome.
we're very excited. I think Aman, do you have any questions? or Alex or anyone. Oh, I don't know if Amon can unmute themselves. Give me 1 second.
Yeah, I have a
Uh,
question while we're
Yeah.
unmuting them on. So you talked a little bit about not using unit tests. Can you comment on that further? Because this is something that we were actually just recently discussing internally. It's about using unit tests to validate, particular modules of our implementation.
Yeah, exactly. So unit tests, so in CleanRL, right? Because we sort of minimize the lines of code, there's not really much room for unit tests because if you want to do unit tests, you have to make them into functions, right? That's how usually you can do unit tests. But I think there are a couple of things that we can do. And I haven't done that yet, but I imagine how that could be done in CleanRL is something that you want to still make the main code base like this, but you want to do unit tests in a super hacky way. So that's sort of the philosophy for CleanRL, is that the core implementation is super simple, but I do all these hacky things, experiment management, all of the complexity or ugly things exist in utilities that is not directly connected to the main implementation. So one thing that I think could work is I'm sort of going to monkey patch the environments, the gym environments, and then when I produce Carpal, it's going to create an instance of my customized version of Carpal that gives deterministic results. Then I can use something like Rumpy to run the file, and I can access things from Rumpy, and I can assert the general advantage estimation gives you some results. Because the point of unit tests is to ensure your implementation is correct in that module, right? So it still has a very good utility. It's just that I think in RL, end-to-end tests are equally important. And because we did a lot of end-to-end tests, we just sort of say, it's okay. The unit test is not that necessary, but we do have an issue. Let me look at it. So this is how it could work, for example. This is not the correct one. Oh, it's in the Hugging Face integration, probably.
oh, CleanRL has Hugging Face integration?
We're adding it, and it's actually quite related to how to add modules in CleanRL.
That's interesting. Yeah, because like the single file stuff felt like it was so similar to what Hugging Face does. Like I would be shocked if they weren't over that on that.
Yeah, it's pretty challenging. Yeah, sorry, I don't know where it is. But there should be an issues.
Anyway, I think we should probably do this offline.
Yeah,
unless
sorry.
you have it like right there.
Yeah, I do want to show, for example, how the integration for Hugging Face is done and how you add modules. So the way that I add modules is a little bit of coconut head. I'll show you what I mean. So because I really don't want to import something CleanRL, I want to keep the single file implementations. So I make it super hacky, where at the end, this is why I stick in the ugly stuff, like importing a modular evaluate function. So it can be done. It just in CleanRL, because I want to keep the simplicity, I hide that at the very end. And it's not always executed unless you specifically ask for it. Yeah, and yeah, thanks for the question on unit tests.
I had a question about performance actually. So when you were looking at JAX, was that just JAX on TPUs or was that also JAX on GPUs?
So that's JAX. For PPO, I only looked at GPU because MPL's XLA interface doesn't support TPU. But for DDPG, we did have benchmarks on GPU versus TPU. So for example, it looks like this. The image is slower than the weights and biases report. So, okay, so you see the VM with the TPU. Don't like this chart. This chart is the sample efficiency chart, so it ensures the implementation is correct. You get the same level of performance, but in terms of the difference between TPU and the GPU, this is what you look at. So with the same hardware, RTX 3060 Ti in DDPG with PyTorch, PyTorch uses 54 minutes, JAX uses 20 minutes, and then TPU uses 42 minutes or so. It could be the case that my machine's CPU is a little bit faster, but I don't know whether this is like TPU is slower than GPU. Yeah, I don't know.
Really
Yeah, that's
surprising, actually.
interesting. Yeah.
Have you like
Yeah,
done like extensive profiling of like why this is?
No, I've not. But I think the TPU machine was from Jaro. He ran this experiment. I think he got the machines from, TensorFlow has this like a research program where if you apply, they gave you like 200 CPU and a lot of TPU machines. So I think he ran it with one of those. But it could be the case that some other experiments are running. I don't know. It's just that I don't own that piece of hardware and don't know what's happening there.
If you want to
I
run
see.
it, we have like tons and tons of TPUs at Carper.
Oh
We
yeah,
have it would be pretty easy for us to get you up and running.
yeah. I mean that'll be amazing. Yeah, because like implementing profile it's pretty simple, right? Because it's single file implementation. You just add a couple lines of code to count the time. You don't have multiple modules and trying to count times in different modules. It's yeah, it's pretty straightforward as well. So
sure.
yeah. So I see Jeff had a question. How many people are actively working on this project? Is there a coordination channel apart from GitHub? Any meetings? Yeah,
Jeff,
so
you're
that's a
unmuted,
really
by the
good
way.
question.
Sorry.
I'm muted, sorry.
No, I sorry, Jeff, you're unmuted if you wanted to talk.
So we do have a Discord channel, but I would say the coordination is sort of asynchronous. So we don't have like weekly meetings or so, partly because we're not really a company, and all of these are mainly run by volunteers. So it's hard to organize weekly meetings. When we first started it, we did have weekly meetings, and that is to say, we want to implement an algorithm per month, so everyone look at the same literature, try to implement it. It was just a lot of work, and we realized implementing algorithms in an example of PPO, there's actually a lot more involved. So we have since transitioned into sort of this asynchronous work collaboration paradigm, if you will, where basically we have a really good contribution guide that says if you're contributing to a new algorithm, and there's a list of things you would need to do. So for example, PPO DNA is a new algorithm that is published in Europe, and we basically say there's a checklist. If you're contributing a new algorithm, you need to add the tracked experiments, you need to add implementation details, specify if any differs from the paper, you need to explain any new log metrics you've added, you need to add links to relate. So we try to make it a streamlined process for everyone who's interested in contributing, so that they know what they're looking for.
It's really interesting.
Yeah, thank you.
I've been hesitant to start adding new RL algorithms to TRLX because we were worried that it was going to bloat the library a lot. especially because optimizing these algorithms for very large language models is non-trivial, and each algorithm probably requires like a month of like an engineer's like full like focus.
Yeah,
So-
and I think it actually, yeah, so I totally agree with that, and I think it's a really good approach. Like in the case of PPO, right? There's just so many things that you can dig into it, like what's shown over here. Like this span across multiple years. I would say it goes from coding some simplified implementation of it to go to creating really good benchmark. There's a lot of things that happens under the hood. The implementation, right? It's relatively easy to come up with the implementation, but if you look at a lot of the PR results, like we're using single file implementations, right? Why are there 23 file changes? It's just because there's so many effort that goes into documentation, benchmarks, and things are done correctly.
That's insane.
Yeah, yeah. Like I mean, this could be easily 1 month of work. So yeah, I totally agree. I think being really focused on PPO would be a good direction. You don't need a lot of fancy algorithm, and I think those, if you add a lot of algorithm, yeah, like you said, it could distract you, waste more engineering efforts, and that might not be a good use of time.
Definitely. Yeah, it's something that's very, very hard to scale. Even though Carper is still very dependent on volunteer efforts. I mean, our volunteers are typically not from RL communities. Interestingly enough, our volunteers are typically people who have experience with large language models and very little RL experience.
Hey, I mean that yeah, and I have no NLP experience, and when I saw corporate AI, it's sort of and having this sort of project to work on ChatGPT, it just looks really cool. And yeah, I think there's a lot of areas, a lot of rooms to grow there. It looks super awesome, and yeah, I would really like to help more. But yeah, it's
No, it's okay.
it's swamped, but yeah.
Yeah. Does anyone else have any questions? Once again, message in the chat if you want me to let you unmute yourself, or you can just put your question in the chat and I'll read it, or Costa will read it. Okay, I'm going to assume that there's no more questions. Okay. Thank you everyone for coming today.